Right. Right. So Drew, just to go through, just to recap what we did in the last session quickly. Do you recall? Do you recall what we did in the last session?
Um, Latent heat,
We did latent
um,
heat.
specific latent heat, um, like of vaporization, fusion.
Right. We looked at heat
uh,
capacity, specific heat capacity,
Yeah,
the formula linking heat capacity, the specific heat capacity. Right. We looked at some questions involving multi-step changes. So I'm talking about questions that involve a change in state first and then a change in temperature. Anytime there's a change in state, there's a temperature change. Talk to me. Anytime there's a change in state itself, there's a temperature change.
no,
Nah. Right? And the easiest way to understand that is imagine holding a block of ice in your hand. The immediate point at which the ice melts is still the same temperature as when it was frozen. Right? So we looked at all of those things. I also showed you the kinetic theory of matter. So today, I want to wrap this up and move on to the gas laws. But before we could do that, we need to look at cooling curves and heating curves. So the best way to do that is with a question, a past paper question, one time. Try into that one time. Where is it? Right, guys. So remind me, when you're changing temperature, one thing, when you're changing state, like let's just say you're going from a liquid to a solid. At the point in which it change state, is there a change in temperature? Yes or no? Anytime you change in state, again, I can't stress this enough. Is there a change in temperature? Is there a change in temperature when you change state? Yes or no?
no.
No, right? No. So keep that in mind and let's do this past paper question together and intuitively understand it. So Drew, give the question a read. Oh, wait, okay, it's already recorded. Good. Yeah, so Drew, give it a read.
As a substance which has a melting point of 80 degrees Celsius is cooled from 90 degrees Celsius to a complete solid at its melting point. Sketch a graph in figure 1 to represent the statement above.
Right. So where does it melt at? At what temperature?
80 degrees Celsius.
Right. So if I were to lower the temperature below 80 degrees Celsius, what state would I be?
Solid,
Exactly. And if I go past the melting point, what would I be?
liquid.
Right. So we are cooling a substance which is at 90 degrees Celsius, right? To a complete solid at its melting point. So let's try to understand this. So, Drew, what temperature am I going to start off at?
Start off at
Yeah. So I'm cooling the substance from what temperature? From
90
what?
degrees
Right.
Celsius.
I'm going to start off at 90 degrees Celsius. This will be called a cooling curve because I'm cooling the temperature of the substance. So for a cooling curve, do you think we're going to have an upward gradient or a downward gradient?
A downward gradient.
Right, because as time passes by, your temperature is decreasing. So negative gradient. Right. So at 90 degrees Celsius, and I'm going to put 80 degrees Celsius somewhere over here. All right. So do you understand that we'll cool, cool, cool until we reach 80? Yeah.
Yeah.
Right. Now at 80, there's going to be a what? A what?
Plateau.
Right. Because it's gonna be at when it reaches 80, it needs to change state. You need energy to change state. And when you're changing state, there's no change in temperature. So as time passes by, there's no change in temperature. All of the energy is being used to rearrange the atomic structure to make it into a solid. right? So after some time has passed, now it's going to keep dropping, dropping, dropping. Right. So talk to me. From 90 to 80 over here, what do you think our state is?
Um, solid.
Solid? Nah.
Wait, not solid, my bad. Liquid.
Liquid, right? Because the melting point is 80 degrees. We started off at a temperature greater than the melting point. So it would have been a liquid over here. And this region over here, that would represent the latent heat of
Latent heater, liquid, the solid,
mhm.
diffusion, and
Exactly, that's fusion. So over here, there's a change in state. So this is liquid to solid, right? And that is LF. All right. And what is the state over here? Talk to me. What do you think the state over here is?
solid.
Right, solid. That was easy or hard?
Oh, it was all right, easy.
That's easy, right? That is easy. So this is a cooling curve. I'll label it. This is a cooling curve. Like it told me, if a cooling curve has a downward gradient, right, a negative gradient. So a heating curve will have a what type of gradient?
Um, Ascending gradient.
Right, going up, right?
Yeah.
And the reason for that is because for a heating curve, I'm actually increasing my temperature with respect to time. So let me give you an example of what we're talking about. So let's look at a heating curve example, right? An unknown substance has a melting point. All right, give me a temperature. So an unknown substance has a melting point of,
100 degrees.
all right. All right, so an unknown substance has a melting point of 100 degrees Celsius and a boiling point of what?
Um, 120.
That's interesting. But sure, sure. This reminded me.
What happened?
No, like it's interesting because think of it from a chemistry standpoint. It takes 100 degrees Celsius for it to begin changing from a solid to a liquid, right? That's the melting point, right? And then we're saying, so that's a lot of energy, right? That's a lot of heat energy. Think about it. You need 100 degrees Celsius to convert from a solid to a liquid. That's the melting point. And then you're saying 20 degrees more is gonna turn into a gas. You understand? You understand how that sounds a little interesting? Think about it.
Yeah, kinda.
Because it's taking real energy, right, to go from a solid to a liquid, the melting point, right? And then it's just taking 20 degrees Celsius more to turn to a gas. Yeah.
Alright.
But I
Boiling point is 250.
okay, yeah, that more reasonable, right? That more reasonable. Question, do you know about things like gallium and mercury?
We haven't gone into that in school, but I know the elements.
All right. So like mercury, right? Mercury has a very low melting point, right? We know that because
Yeah,
at room temperature, mercury is what?
a liquid.
Exactly. So it wouldn't take because it's so easy to melt, it would be relatively easy to boil as well, if you understand what I'm saying.
Yeah.
Yeah. Right. But if something takes a lot of energy to melt, more than likely it's gonna take a lot of energy to reach your boiling point as well. Right? So this 250 degrees Celsius make more sense. Right? So unknown substance has a melting point of 100 degrees Celsius and a boiling point of 250 degrees Celsius. If its initial temperature, if its initial temperature is they want to be what do you want to let its initial temperature be?
Um, 50 degrees.
All right. If its initial temperature is 50 degrees Celsius, um, draw and sketch. Right? Sketch the heating curve as heat is added to the system. Heat is added. Right. So what do you think is going to go on my y-axis?
Temperature.
Yeah, temperature is going to go on my y-axis, right? And in this instance, my temperature is going to be in degrees Celsius, right?
Yeah.
Okay. What do you think is going to go on my I mean my x-axis? X-axis.
Time.
Time, right? At what temperature am I going to start off at?
50 degrees Celsius.
All right, 50 degrees Celsius. This is a sketch. So I could call this 50 degrees Celsius if I want, right? And what are the other main points I need to mark down?
The melting point and the boiling point.
Great. What is the melting point?
100 degrees Celsius.
Great. So I'll put 100 degrees Celsius over here. What is the boiling point?
250
Right,
degrees Celsius.
right. Okay, I know how to put the Celsius, right? Because it's understood to be Celsius. Okay, so you understand what I draw so far, right? Talk some more.
Yeah.
Okay. Now we are starting at 50 degrees Celsius and we are adding heat to that. So I'm going to draw an upwards gradient and I'm going to stop when I reach 100. So from 50 to 100, what is your state? What is your state from 50 to
Um,
100?
Solid.
Right. You're a solid, right? Now over here, what's going to happen?
Melting.
Right. Is melting an immediate process or does that take energy?
Takes energy.
Right. So it's going to plateau over here. Right. It's not going to turn to a liquid immediately. Right. But when the process does get completed, now it is a liquid. Where else is it going to plateau at?
Um, at 250.
Yeah. And at 250, it's going to experience a change in state from a liquid to,
I guess.
right. Okay. Great. And you keep on heating it until it's into a superheated vapor. I'm not sure if you're gonna do mechanical engineering or electrical engineering. If you do that, you'll learn about superheated vapor and whatnot when you do thermodynamics. Yeah, good luck. What you planning on doing though? I have a question. Like, what you planning on doing?
I'm not completely sure yet, but I was leaning towards medicine.
Medicine? Oh, you give engineering vibes. I don't get in medicine. I don't get in medicine. What's
Why? Because I didn't pure.
Yeah, I mean, I don't know. I just getting the engineering vibe. Maybe I'm biased. I am biased. I am biased. Because like I was
You have
going
an
to,
engineering degree.
yeah, I was going to do well I'm finishing my bachelor's actually in electrical and computer engineering. I was going to do neuro neuroscience and I was like, I'm gonna jump ship. Jump ship last minute. Yeah. What you want to do in medicine though?
I'm not sure yet.
Or something in medicine. But
Um, and you could specialize in cardiology.
I don't know too much about medicine. I'll be honest. I don't really know much about medicine. If you ask me about engineering and maths something, yeah. But I can help you
True.
out.
Oh,
I could give you contacts for people that could help you because I have a lot of colleagues and people I know that do medicine. So if you ever
but
need any
you think the
advice,
yeah,
yeah. Do I think
the med school in UE, you think it like is a good school to go to or to go elsewhere?
I don't really have much experience with that. I can't really tell you. I could give you the contact for persons I would know, right? But you know, escape any maths. You have to do maths in that.
No, I like maths. Maths is a normal subject.
Okay, cool. But why you do engineering? You love engineering. You love engineering.
But that was kind of well. I need physics to to become a medicine major or whatever. I
So
thought
that,
I didn't need it, and at the time, I just didn't like the teacher in my school, so I didn't go.
oh, baby boy.
But I thought I would have liked physics really because I have maths in it.
Yeah, physics is fun. Physics is
I
fun.
should have do it.
Yeah, because you see how easy physics is, right? Physics is like quote unquote common. Like it's not that hard to follow.
Yeah, it takes in some chemistry, some maths. Except I don't know about I hear what is magnetism is a hard topic.
I wouldn't say that. I wouldn't say that. I go into specialize in power systems and energy, which is a lot of actually is a lot of magnetism, induction,
And I
Israel.
hear some of my like classmates talking about logic gates.
Yeah,
There's real talk about
like logic gates is so buns that I don't like logic gates. I don't like logic
it
gates.
harder.
No, it's not hard, it's just very annoying. It's annoying.
How you mean annoying?
Like in maths, right?
Like it
You're doing maths for the numbers.
yeah.
You're doing maths for the numbers. You're doing maths because you like to be logical and you like to go on a journey. So when you had to do them proof questions and you had to write, okay, the base case was valid, and as such, we assumed n was equal to k for n is a for n is an element of real numbers, and then based on this assumption, we found that n is equal to k plus one was valid. Therefore, the statement S of n is valid. You're not doing maths to write all of that, you know. So when you had to like write a
And
little,
yeah, I know what you mean. I know what you mean.
it's a similar
The
kind of
point to my English.
it's a similar kind of thing. I just don't like it much. It's not hard. It's just annoying. And with a
You had to do all that for
diagram,
logic gates.
no, for logic gates, you have to just keep drawing a bunch of diagrams and see where it's connected, and it's just annoying. And you have to draw real tables and thing. It's very, very similar to truth tables, which you would have
Oh,
done.
two tables.
Yeah, which you would have done. Because truth tables is an application of logic gates.
Two
Hmm.
tables, it all right, good. I like two tables.
Serious?
It's easy maths. Except for um the laws when you had
Yeah, like
to
the
prove it or
Morgans.
whatever, absorption laws and shit. No, oh
Like,
my bad.
yeah. Yeah,
But
it's like
absorption laws and what's the other ones? Identity laws.
yeah.
It kind of like trig proofs.
It is. It is kind of
So
complex.
I would like to see that.
Yeah, well,
Yeah.
good luck. Right, so let me continue. So Nikolai,
Mm-hmm.
I saw Nikolai join and then he just dashed out. Becca, talk to me. I know you told me that you're not home. That's why I'm not calling on you much, because I'm not sure if you have anything to write on. But Becca, do you understand that a heating curve is just you heating up a substance? If a substance,
Yeah.
so if a substance starts off being a solid and you apply heat, eventually it's going to turn to a liquid. And if you keep on adding heat, eventually it's going to turn to a gas. But what I'm seeing is during the melting point and the boiling point, it's going to be a plateau where energy is used to rearrange the molecules. So you're not going to experience a change in temperature when you're changing state. It's going to be flat, right? So latent heat of fusion and latent heat of vaporization comes into play here, right? Because
Okay.
what do you think the state is over here? What do you think the state is
Um,
over there?
it would be a liquid,
Great. And the state over here?
a gas?
Right. And what about the state over here? Is there a specific state?
No, that's when it's changing.
right? And what latent heat would I use for that?
From what? Solid to liquid?
Yeah, solid to liquid.
Fusion?
Right, latent heat of fusion. Drew, this is liquid to gas. What type of fusion would I use? I mean, what type of latent heat I would use there?
Vaporization.
Great. So guys, are we okay with coolant curves and heating curves? Oh no, guys, is it hard or?
No, I understand it.
All right. If all I do in chemistry, are they supposed to do this? I swear when I was in secondary school, I had to do labs on coolant curves and heating curves. I swear. Drew, you're sure you never do this in chemistry?
No, sir, we do this in chemistry.
Okay, okay, yeah, yeah. That's why I know like this is chemistry stuff, right?
Yeah.
Okay.
We
Let's
never do a
quickly
lab on it though.
oh well let me quickly do this question, then we'll move on to passive properties. So Ambika, read question C for me quickly.
A physicist converted 2 kg of water at 37 degrees Celsius to
This
steam at 100 degrees Celsius, assuming no heat is lost. Calculate the amount of energy needed to heat the water to 100 degrees Celsius.
Right. So if we want to heat the water to 100 degrees Celsius, are we changing the temperature or are we changing the state?
The temperature.
Just the temperature, right? Just the temperature. Right. Because I said to heat water to 100 degrees Celsius. So this is a change in temperature. Change in temperature. What formula do we use if there's a change in temperature alone? Talk to me. What formula do I use when there's a change in temperature?
That's the one with delta and theta, right?
Right, because delta means change. So change in temperature. That's what delta theta means. Change in temperature. So E is equal to what? Talk to Mohammed.
MC delta theta.
Right, MC delta theta. Right, and well, we know delta theta means change in temperature. We know delta theta means change in temperature. Right? So is the mass already given to us in kg?
Yeah.
Yeah, so the mass is 2, right? Do we know what the specific heat capacity is? Waiter, it's supposed to be given to us. Yeah, look it was given to us over here. So the specific heat capacity is 4200, is always 4200 if we're dealing with water, always, right? So the specific heat capacity is 4200. So 4200. And to find the change in temperature, that's going to be 100 minus what?
37.
Right. So plug that into your calculator and let me know what you get.
I don't have a calculator, you know.
Quick maths. Amiga, quick maths. Quick maths. Mental maths. All right. Okay. Drew or Nikolai? Nikolai, you good? I see like the Wi-Fi giving you some trouble there.
Yeah, no, I don't know.
Oh. Everything all right with you otherwise?
Yeah, I could just the internet getting trouble.
Ah, okay, okay. Well, Nikolai, if you have a calculator, I'll wait to plug this in and let me know what you're getting.
Okay.
Yeah.
The two in the bracket is how much are the 4,000 and about that is a second. So I like something separate.
Okay. This 2 over here means that we're multiplying 2 by the 4200 and we're multiplying that by 100 minus 37. That's what we're doing. So this means 2 by 4200 by this. All of that is multiplication. I'm not sure if that's what he was asking.
Yeah, that's
Yeah,
what I
I
was
get
asking.
Let me know what you get. So plug it into your calculator and let me know what you get.
529200.
529200. And Nikolai,
Yeah.
since we're finding for energy over here, what is the units for energy? What do we measure energy in?
Joules.
Yeah, joules. So it took 529,200 joules to convert water at 37 degrees Celsius to water at 100 degrees Celsius. There was no conversion, it just raising the temperature. And Drew, you can believe this is 4 marks? You know how hard they would have to look for 4 marks in pure maths?
Yes, this is looking real nice, you know.
I tell you, physics is light work. All right, part 2. Here's a read from now.
Um, Calculate the amount of energy needed to heat the water from 100 degrees Celsius to steam at 100 degrees Celsius.
Ah, so Drew, stay quiet. I feel like you know the answer. Nikolai, talk to me. In the second question, are we experiencing a change in temperature or a change in state? Talk to me. What do you think we're
A
experiencing?
change in state.
A change in what?
State, a change
The,
in state.
Right, a change in state. So what would I use then if I'm going from water to steam? That's latent heat at what? It have latent heat of fusion and it have latent heat of vaporization. Which one do you think we would use?
Vaporization.
Right. Do you remember the formula for that?
Yeah.
Talk to
Hold
me.
on. I'm looking inside my book together.
All right. Drew, you remember the formula by chance?
I'm not gonna lie, I don't remember it, but I just read it just now.
What if
So
I
it's
told you
mass.
yeah,
Huh?
us? What if I told you there was a way to figure it out without even knowing the formula? There's a very easy way, right? All of these formulas contain mass in them because do we understand that a given
It's
amount of
specific.
mass, yeah, yeah, and a given amount of mass would release a specific amount of energy, or conversely, you would need a certain amount of energy to raise the temperature for a given mass. All of these energy calculations are dependent on the mass. Because think about it, Drew. And the greater the mass, you need more energy. Can you see the
Yeah.
proportionality? You can see the direct proportionality, right? The greater the mass, the more energy I'll need to change the temperature. So all of these formulas will contain mass logically. So that's we could rule that one out. We could put M, right? You could put M, right? Great. And M is measured in kg. Now, Drew, aren't we vaporizing the water? We're turning the water into steam, right?
Yeah.
Yeah. So, do you remember what the latent heat of vaporization is?
What it is?
Yeah, the specific one.
The meaning?
Yeah, it tells us the amount of heat energy you would need to.
Um, to change the state of a substance from liquid to gas or from liquid to gas at a constant temperature,
Right.
at a certain mass.
Right.
Whoa.
For 1 kilogram. For one
Yeah.
kilogram. Right. Now, watch this. Watch this. If you look at the specific latent heat of vaporization and its corresponding units, the units for that is joules per kg, yeah? See that? It's joules per kg. So what would happen if now I multiply these units by mass, which is kg? What would happen? What would happen?
Yeah. The kgs will cancel.
To leave you with,
The joules.
which is energy, right? So even if you were to
Mm-hmm.
forget this formula, I don't think is the end of the world. You could figure it out. You could figure it out. So, Nikolai, hear what I'm saying, right? Nikolai, if you forget the formula, look at what they gave you. So, Nikolai, can we see that they gave you the latency of vaporization? They would have given you that for some reason, no? They would not just give it that for style. So, Nikolai, I would implore you to look at the units. What are the units for this? What are the units, Nikolai?
kg.
is joules,
Joules and kilograms.
not just kilograms, but kg to the power minus one. So Nikolai, anytime you see something raised to the power minus one, that could go in the denominator. So you see this? I could interpret that as joules per kg. You with me?
Yeah.
And Nikolai, if I wanted to get energy, energy is measured in what? What is energy measured in? Remind me. Energy is
Energy.
energy is measured in what are the
Energy.
units for energy?
Energy is measured in joules.
Joules, right? So talk to me, Nikolai. What would I need to multiply by this to cancel off with this to leave me with just energy? I have to multiply that by what?
You don't multiply that by the next kg.
Exactly. And kg is a measure of what? What does kg measure?
The mass per kilogram.
Exactly, right? So Nikolai, just like that, we were able to figure out the formula. Because what is this? Well, that is the latent heat of vaporization, right? The specific latent heat of vaporization. And what is this? This is mass. So we just came up with the formula. E is equal to mLV. So in physics, if you forget the formula, it's not the end of the world. Just look at the units, guys. You're not chopped. You figure it out, right? So yeah, Nikolai, the formula is E is equal to mLV. What was the mass of the water? What was the mass of the water?
2 kg.
Right, the mass was 2 kg. And the latent heat of vaporization was 2.3 by 10 to the power 6. Right, so plug that into the calculator and let me know what you're getting. Well, you don't need a calculator to do this one. 2 by 2.3 is what? What is 2 by 2.3? Talk to me, guys. What is 2 by 2.3?
4.6.
Right, so this is just going to be 4.6 multiplied by 10 to the power 6. What? What's the units?
J. Joule
Yeah.
or kg.
Nah, not kg and not kg. Right, remember, we're finding for energy. Energy. And if you're confused, look at the units, right? We measure M in kg, right? We measure M in kg, and you multiply that by latent heat of vaporization. Nikolai, do you remember the units for latent heat of vaporization? Specific latent heat of vaporization?
Yeah. I believe it was
It was joules over Kelvin.
joules over kg.
Yeah, and watch the kgs would cancel off to leave you with what?
Energy alone or joules.
Exactly. So the units has to be joules, right? Yeah. And guys, believe it or not, right? Believe it or not, that's 10 marks. No, that's 9 marks, you know. That's 9 marks so far. So easy 9 marks. Drew, what do you think? Hard 9 marks or like easy 9 marks?
Yeah, normal.
Yeah, that's an easy 9 marks. Okay, and the last question they would ask you is, what is the total energy? How would I find the total energy? Tell me fast.
Yeah, I had both of them.
Right. Plug that into your calculator and let me know what you're getting.
Um, 51, 29, 200.
51, 29, 200,
Yeah.
right? And I'll be joules. Is there anybody confused by cooling curves, heating curves, and the regular questions with change in temperature, change in state, and total energy? I don't know if you guys confused by that any slightest. Are any of you all confused? Talk to me. Olio, don't leave me hanging like this now. If Olio understand,
Nah,
talk to me.
that's it. I
You good?
understand.
All right. Ambika, Drew, are they good?
I understand as well.
Yeah. Yes, sir.
All right. So now we need to look at the passive properties and how it affects heat. Okay. Guys, let's think logically, right? What color do you think absorbs the most heat?
Black.
Black, right? So the properties we need to look at is we need to look at absorb absorb. Wait, we need to look at emittance, right? Absorption, radiation, right? And reflection. So I'm going to list a bunch of properties and I want you to tell me what it's best at. Okay, so black. Black is the best at absorbing heat. Yes or no?
Yeah.
Yeah, so I'll put black in absorption, right? It's really good at absorbing heat. I have a question, guys. If something is really good at absorbing heat, wouldn't it contain a lot of heat? Drew, talk to me. If something could absorb a lot of heat, what does that mean? Uh,
I'll make a whole lot of heat.
exactly, it could hold a lot of heat. And if it's holding a lot of heat, wouldn't it give off that heat as radiation?
Yeah.
Exactly. So black materials are very good absorbers of heat, and they're very good emitters of heat as well. Why? Because they store a lot of heat. Do you understand that reasoning? Yeah or no? Ambika, do you understand why I'm saying black are good absorbers of heat, as well as good emitters or radiators of heat?
Yeah, I understand.
All right. Okay, white. Talk to my guys. White. What is white good at?
It
Reflecting.
reflecting.
Right. White is good at reflecting short-wave radiation or long-wave radiation. It's good at that. It's good at reflecting heat. Okay, what about rough surfaces? Rough surfaces. Do you think rough surfaces absorb heat, reflect heat, or emit heat?
Reflect.
Nah, nah. Max, that question, Nikolai. When you hear the word matte, do you think of shiny or dull? Matte.
Dong.
Wait, let me reiterate that. If you hear, if a car is painted in matte black, when you pass your hand against the paint, does it feel smooth or does it feel a little rough?
Mm, you go feel good.
Nah, it will be a little rough because it's absorbing light.
Mm.
Yeah. So if we're talking about rough, if a surface is rough, it makes it a good absorber of heat as well as a good emitter of heat. Okay, next thing. If a surface is shiny, what do you think that makes it good at? Nikolai, shiny. Fine,
Reflecting.
right? Reflective. Okay, what are some other obvious ones? Okay, if a surface is dull, if a surface is dull, do you know what dull means? It's the opposite of shiny. So if a surface is dull, do you think it's gonna absorb heat or reflect heat?
Absorb it.
Um, Drew, do you agree? If I say we have a dull surface,
Yes, sir.
okay, so I'm going to put dull by absorption and emittance. Okay. Surface area now. Guys, if we have a high surface area, do you think that would make me a good absorber, reflector, or emitter? Or which one? If I have a very high surface area. If something has a very high surface area, it makes it susceptible to doing what to heat. A high surface area. Drew, if something has a large surface area, right? Very large surface area, do you think it's going to reflect heat, absorb heat, or emit heat?
Um, Large surface area.
Yeah,
I think you absorb it that better.
yeah, exactly. Because it has a large surface area, right? It could absorb a lot of heat, right? Okay, if something has a small surface area, do you think it would be as good of an absorber? Talk to my guys. If something had a small surface area, Nikolai, if something had a small surface area, do you think you'd be able to absorb as much heat?
Nah,
Nah, right?
not
Okay,
as
so
much.
these are the most basic properties you need to be familiar with. So I'm going to allow you guys to take a screenshot of this. Right, so take a screenshot of this. You need to be familiar with this. Right, you need to be familiar with this. So absorption of heat, which is radiation, emission, reflection, and how it behaves. So take a screenshot of this. When you have the screenshot copied down, well, can't say copy down. When you have the screenshot, let me know so I can move on to a past paper question.
Yeah, it's good.
Right, Drew, what about you?
Yeah, I guess.
Ambika, I know you're not home. Did
Have
you?
it too.
Okay, let's look at a past paper question now. Let's go. Right. So, Drew, I'd like you to read this for me.
Four factors of the surface area of a material on which the absorption and emission of radiation depend are texture, rough or smooth, na nature, dull or shiny, color, black or white, area, large or small. State with a reason the appropriate characteristics of two of the above factors in the design of a car radiator.
So Drew, if you want to make a car radiator, what is the purpose of that?
Um, I'm not sure entirely though, but it's not to cool the engine bay.
Right, it's to cool the
I
engine.
could be
Now,
wrong.
no, no, you're right, right? You want to cool the engine, right? Now, if you want to cool the engine, do you want to keep the heat in the engine or you want to absorb the heat from the engine?
We want to absorb it.
Exactly. You want to pull heat from the engine and dump it to your surroundings. So you need to be a good absorber and a good what?
Um, Radiator. Well, emitter.
Exactly. Right? So what properties here would make me a good absorber and a good emitter? What's the easiest choice?
Um, a good absorber and emitter.
Yes.
Like
Tech.
one characteristic fit.
Yeah.
So dull. A dull surface.
Yeah, but I really want to hear black, eh? But you're not wrong. Black is the most obvious one. Black is the most obvious one.
Oh, right, right. I was just thinking black is only absorb.
Nah, think about it like this,
My
Drew.
bad.
If something can absorb plenty heat, right? If something is absorbing real heat, and if you touch it, you're gonna get burnt. Think about that.
Yeah.
And if that is the case, right, wouldn't that mean that it would have radiated or emitted a lot of heat at the point of contact?
Mm-hmm.
Yeah, yeah. You ever wonder why some like frying pans and whatnot is black. Uh, This is why. And some of them shiny, right? But some of them black as well. If it's black, it has a higher
Wait,
chance of
why some of them shiny?
some of them shiny. I actually not sure no. I think it's because it's just metal. It's metal, so it really doesn't affect the properties much, right? Because
Okay.
if something is metal, is naturally a good conductor of heat because of the mobile electrons. And most,
Mm-hmm.
if not all pans are made out of metal. If you want it to be even more conductive though, you paint it black, right? I guess it will make a meaningful difference, Drew. It don't make a meaningful difference because they're gonna be in direct contact with heat anyways. Yeah. Right?
Alright.
But the first thing we're gonna put is um black. Right? So it should be painted black. Why? This would increase the heat absorbed from the engine as well as emitting the heat to the surroundings. Let me know if that makes sense. So I'm saying I should paint the car radiator black, Nikolai. Don't we know that black have really good absorbers of heat as well as good emitters of heat because they can absorb so much heat?
Yeah, it
Right.
would.
So, Nikolai, I'm saying we should use black because it's going to absorb the heat from the engine, right? And it's also going to emit the heat to the surroundings. Does that make sense?
Yeah, it does make sense.
Right? Nikolai, do you think, okay, which other property would make something a good car radiator, a good radiator of heat?
A large surface area.
Exactly. That's what I would say too. A large surface area. Drew, think about it. You want, isn't the radiator placed right next to the engine? Drew, isn't the radiator placed right next to the engine?
Yes, sir.
Yeah, so you want it to have a large surface area so it could absorb as much heat from the engine, right, to dump it to the surroundings. Right? So now some other properties that you could have mentioned would have been rough. You could have said rough. You could have said dull, right? We already mentioned black and large surface area. Do we understand why we were thinking to pick these properties? Come on.
Mm-hmm.
All right, so let's continue. Okay, our roof now. Do you want heat to be absorbed into your home, or do you think you want heat to be radiated or reflected away from your home? Talk to me. Guys, what do you all think? Nikolai, do you want
Well,
the
it reflected.
yeah, you want the heat to be reflected away from your home so your home doesn't get hot. So what is the number one property it should be? It should be rough, smooth, shiny. It should be shiny,
Shiny, smooth.
right? It should
Shiny
be
and smooth.
right. Works. So I'm being specific here. If you have a shiny roof, it's going to reflect the IR waves. By the way, IR stands for infrared, right? Infrared and infrared rays are the rays that actually carry heat. So reflects infrared radiation. Right, right, and keeps the home cool. Right, Drew, what's another property that I should use for my Caribbean home? The roof of the Caribbean home.
When you say shiny already?
Yeah, such an already.
Um, Smooth surface.
Yeah, a smooth surface could work. Right? A smooth surface could definitely work. Or was there even better one to use? Hmm.
Um,
I mean,
White.
you still get it correct, right? But we're looking for the most appropriate answers because it said appropriate characteristics. So white. Because white, what does white do? Does white absorb heat or reflect heat?
Reflect.
Exactly. Good. Let's off. When we do waves and optics, you guys will understand what's on the electromagnetic spectrum, the EM spectrum, right? Radio waves, ultraviolet, infrared, visible, right? You'll see all of that. But for now, I just want you to know that infrared radiation is radiation that carries heat, right? Drew, did you know that? That infrared radiation was the type of radiation that carries heat?
Nah, not really, to be honest.
You thought it was UV or
No,
no?
I didn't think it was UV. It never really crossed my mind. I thought maybe all of them gave heat.
Not quite. Visible doesn't necessarily give heat. It's just light energy, right? Um,
So
UV.
when you're like, I have a question.
Mhm. Talk to me.
So light, the visible light do give heat,
No. Right, what are
but
we doing?
but a light bulb, like when you touch a light bulb, it'll be hot
Okay, you know why? It's not because of okay,
because of the yeah,
yeah, talk to me. I want to hear a
it's
reason.
from something else.
Yes, it's from something else. I'm gonna ask that question. Why do you think people switch from filament bulbs to LED bulbs?
I don't know.
Okay, it's because filament bulbs are very inefficient. And how filament bulbs work, it actually works by having a short circuit. That's how it works. So I'm not sure if you ever looked at a filament bulb before, but it looks something like this. You'd have two wires here. You ever see something like that? A filament bulb or not?
Yeah, like in movies.
Exactly in movies. So what happens, right, Drew, is that the current passes through the loop and it creates a short circuit, and so a lot of current passes through here and it generates a lot of heat, right? If you continue to do physics, you learn about Planck's law and what happens when you heat up objects. Now, Drew, you should know this. You ever watch those videos where it's like 1,000-degree ball versus like a foam? You know what I'm talking about? Like where they heat up something and they drop it.
Oh yeah, I see that.
Okay. Anytime you heat up an object, it starts to what? It starts to emit what?
Energy.
Light. I wanted to hear light. Think about it.
Oh
When you heat up like a metal spoon or a metal knife, it starts to glow red, right?
yeah,
Yeah. So okay. In that instance, we create light, but is light the primary product, or is it just a byproduct of heating?
it's just a byproduct.
Exactly, it's a byproduct of heating. So, if the main goal here is to generate light, it's not very efficient because a lot of that energy is going to be generated as heat energy, not light energy. But
Also, the
wait,
light in this bulb is just a byproduct.
exactly, because this is going to get really hot and it's going to start to glow because of the heat, and that's going to create light. So light is not the main product here, it's heat. That's why it gets hot.
Oh,
If you
but the
compare
LEDs don't get hot.
Yeah, the LEDs are a lot more efficient. They stand for light emitting diodes, and their primary goal and their primary use is to make light. But it still has some inefficiencies and it still creates heat. It still creates heat, right? But it's a lot more efficient. Yeah, no system is ever 100% efficient, right? But LEDs are a lot more efficient than the filament bulb option. Yeah. So I hope you understand that,
Oh,
right?
all right. Yeah,
So
yeah.
it will create, think about it. The filament bulb, it will create visible light on the spectrum, but it will also create infrared radiation, which is perceived as heat. So if you understand what I'm saying, light by itself is not heat. It's how you create the light. Yeah. Awesome. So I hope you understand this. Now we're going to move on to the greenhouse effect, right? The greenhouse effect. Okay, so you guys can take a screenshot of this. And we're going to move on to the greenhouse effect. Do any of you guys remember the greenhouse effect from doing agriculture and like until I supposed to learn in next year? I don't know, that's a while ago. Or I think it was supposed to be in science. If any of you guys did that, integrated science. Are they know about the greenhouse effect?
Yeah, I think so.
All right, Nikolai, let me give you the simplest example, right? You ever park up a car, right? Well, I know you're young. I don't know if you just drive, but you ever park up a car and you park up a car, you come back in the car, you can't real hot, you can't even touch the steering wheel. You know what I'm talking about?
Yeah, I would.
Right. So what would happen is the short wavelength infrared radiation emitted from the sun is going to pass through the glass. I'm talking about heat energy, right? So Nikolai, the heat energy is going to pass through the glass. It's going to warm everything in the car, right? But the heat energy, okay, think of it like this. So Nikolai, isn't the sun very powerful? Isn't the sun extremely powerful?
Yeah.
Right. So the sun
Yeah.
sends out a specific amount of heat energy that enters your car right through the glass, and then it heats up everything on the inside. So Nikolai, and the heat would heat up the seats, it would heat up the steering wheel, whatnot.
Yeah, we top everything.
It would heat up everything. Now talk to me. What's going to emit more heat? The seat, the steering wheel, or the sun?
The sun going make the most heat.
Exactly. So what I'm saying, right, Nikolai? Yes, you're gonna heat up everything inside the car, but it's not gonna have so much energy as to the level that came in the car. And hot objects would emit heat. And you know that? They would emit a certain amount of heat.
Yeah.
Yeah, like if you heat up something and you put your hand close to it, aren't you gonna feel the heat?
You will feel the heat.
Exactly. But when the large amount of heat energy enters in the car and it heats up the seat, do you think the seat and the steering wheel is gonna emit a crazy amount of heat energy? Or is it gonna emit like a very faint amount of heat?
A faint amount.
Right, but if you touch it, it'll be hot, right?
Yep.
Exactly. So, Nikolai, remember how we just now talked about how it would emit a very small amount of heat energy? You would feel the heat, right? But if you put your hand a little distance, would you feel the heat strongly?
Nope. You won't feel
No.
it strongly.
No. So that re-emitted heat energy, do you think it's strong enough to escape through the glass?
Nah.
Nah. So you know what happens? Over time, it just builds up. It just builds up in the car.
So it is mixed up.
Say that again?
I see, so basically just be trapped inside the car.
Exactly. And that's the whole concept of the greenhouse effect, you know. That's the whole concept. Yeah, that's it. So I'll give you all some notes to copy down. I trust that everybody has this and we understand this. Right? So let's move on to the greenhouse effect now. So this is the properties of the greenhouse effect right here. Right, so Drew, I just want to run through the greenhouse effect with you one more time, just to make sure you fully understand it in its entirety. Right. Okay, so Drew, the best example is a car, right? Drew, when you leave a car parked in the sun, right? When you come back in the car, does it be hot or cold?
Hot too.
Right, it is hot. Now, we just spoke about how visible light doesn't give off heat, right? It's actually infrared radiation that gives off heat. So we say that infrared radiation is actually short wavelength radiation, right? So, Drew, I want you to understand that the sun, right? So, the sun is going to emit infrared waves, which is short wavelength radiation. It has very high penetrative abilities and it has high energy, right? So, infrared waves, that's the heat from the sun. Isn't the sun also going to emit visible light and whatnot?
Yes, sir.
Yeah, but the visible light is not what's carrying the heat. It's the infrared waves that is carrying the heat. Right. So Drew, the infrared radiation emitted from the sun is gonna have a great amount of energy. And it's gonna be able to pass through glass, paper, wood. It's very, very strong. So Drew, if you park your car in the sun, aren't these waves emitted by the sun going to enter in the car through the glass?
Yes, sir.
Yeah, it's gonna enter in through the glass. So we understand in that. And it's gonna heat up everything on the inside, yeah?
Mm-hmm.
Right. Now, when it heats up everything on the inside,
Sorry, yes, sir. 1 second.
okay, no problem.
Yes, sir.
Yeah. So it's gonna heat up everything inside of the car. Now, when it heats up everything inside of the car, some energy is gonna be lost, right? Think about it, Drew. Isn't most of the energy gonna be absorbed by what's on the inside of the car? So like
Yes, sir.
the seat's gonna absorb the heat, the steering wheel gonna absorb the heat, everything gonna absorb the heat. So the remaining heat, right? The residual heat. Do you think it's gonna be a lot? Think about it.
No.
No. Another way to think about it, everything on the inside is gonna get heated up. But is it gonna get heated up to the degree where if you put your hand close by the seat, are you gonna feel the heat? It's gonna be like really strong or weak.
Nah.
It's not gonna be that strong, right? It's only if you touch it, you would feel the heat. But long story short, Drew, if it's gonna heat up everything on the inside, but it's not gonna heat up to the point where it's gonna emit a very strong amount of heat. If you understand what I'm saying.
Yeah.
And this
Yeah.
is when you touch the steering wheel, you just feel how hot it is.
Mm-hmm.
If you put your hand like 6 inches away from the steering wheel, you're gonna feel the heat.
Nah.
Nah. So what happens, right, is the re-emitted heat, right, being emitted from the objects that was heated up on the inside of the car is not going to be as strong as the energy that entered in. So Drew, this re-emitted heat energy from the seats and the steering wheel, can we both agree it's not going to be that strong? It's not going to be that strong, right? So if it's not that strong, do you think it's going to be able to escape through the glass now?
Nah.
Now think about it. Even if you put your hand like 6 inches away, you're not even feeling that. So the energy not even making it that far. So you think it's gonna have enough energy to escape through the glass? No.
Mm.
So Drew, what's happening is short wavelength infrared radiation is entering through the glass. It's heating up everything on the inside, and what's heated up is going to re-emit a certain amount of heat energy. But it's not going to be enough to escape through the glass. And over time, it builds up on the inside as heat. So, hope you
Wait,
understand
sir.
that.
I understand, but I just had a question. If the heat, let me say hypothetically, right?
Mm-hmm.
It might happen, but hypothetically, if it get enough to the point where it surpasses the amount of energy given in, and it could escape,
But that can happen. You want to know why that can happen?
why?
Okay, you're comparing the sun to, you're comparing the
In the
energy.
inside of a car, I know.
Yeah, yeah. But if it does reach,
I just saying,
no, but
let me see. It
it's,
had the sun, right?
yeah.
And then inside the car, it have a sun too.
The only way I could see that working is like, okay, if your car catch a fire and have like an active fire in the car, then heat will be emitted back to the surroundings. But you would need a
So
lot
the
of,
fire would have, all right, yeah.
yeah, yeah. The sun is very far away, right? The sun is like far away, but it still gives us a great amount of energy. So that amount of energy the sun is emitting is still very significant. But when it enters in through the glass,
Okay.
it heats up everything, and most of the energy is absorbed by what's being heated up. So when it enters the car, it's not going to be able to emit much heat after. So the emitted heat is very low.
Okay.
But if you did have something inside the car that was actively being heated up, other than just the sun,
I know.
like we just say you had I don't know, uh like
So if it had a fire and it was close enough to the glass, it would be able to escape.
for sure you'd be able to escape, right? It'd be able to escape. But your statement there where you was saying that what if it reached more on the inside than what was coming in? That would break the law of thermodynamics. It just don't make sense. The amount of energy
I
coming
just
in,
yeah.
it has
I
to
was
be
just
more
trying
than
to
the
like
even. Yeah,
my bad.
you was trying to
I was just trying to compare it to because I do physics, right? I was just trying to compare it to like diffusion
mm,
or osmosis in a sense. If it had enough on the other side, it would try to even off.
exactly no,
But it's not like that.
no, it is like that, right? That is one of the laws for thermodynamics. Heat always goes from an area of like higher temperature to area of lower temperature. So that's the temperature gradient, right? What I'm saying is the energy is so much from the sun, right? It carries so much energy, right, that it's going to enter in and it's going to warm the car till the heat levels are comparable. But
Yeah, okay.
it can't get hotter than the input, if that makes sense,
Yeah,
right?
yeah, that makes sense.
If I'm supplying, say, 100 watts of power, then the input, the energy that's being used, it can't be more than that.
Yeah, only if it had something else in the car
Exactly. Only
that
if it
was
had,
given off heat.
yes, only if it had like an external factor that was actively giving off heat, then it would be able to
Ah,
break the rules. And it wouldn't
I
even
still
be breaking the
understand.
rules.
Thanks.
No problem. And it wouldn't even be breaking the rules, right? Because you'd have an external source of energy, right? Yeah. So let's look at this example and I'll give you all the chance to copy it down. So figure 7 shows a section of a solar water heater which utilizes a greenhouse glass house effect in its operation. So we went through the concept, right? We went through the concept. So let me show you what happens. So over here, we have a black collector plate, right? And we have a glass plate on top, and we have some type of enclosure. So imagine you have a box, right, guys? Imagine you have a glass box. You have a glass box, right? And they have a copper plate. Okay, they didn't say a copper plate. They have a black collector plate at the bottom. So let me see if I can do a three-dimensional drawing of this thing. Let's see. Could I do that? Right. So first things first, guys, if you have a glass a glass box and I put it in the sun, what do you think gonna happen? Talk to my guys. If I take a glass box and I put it in the sun, what's gonna happen to inside the glass box?
Inside the glass will get hot.
Yeah, because we know what's gonna happen, right? The heat is gonna enter through the glass, but it's not gonna be able to escape. So inside it's just gonna get really, really hot. And to channel this, what they are doing is they are putting a black collector plate at the bottom. I have a question, guys. Why would they put a black plate at the bottom of the glass box? What do we know about black materials?
It does absorb heat.
Exactly, they just absorb heat. So this is what is happening. The sun, I had to be specific, right? You have to say that the short wavelength radiation is entering through the glass, right? And it's going to be absorbed by the black collector plate. Do we understand now so far? So the heat energy from the sun is entering the glass and it's going to warm the black surface in the bottom. Yeah or no? You understand that? Talk to my guy.
Mm-hmm.
Right.
Yeah.
Now, what are they doing here? So you have the glass here, you have the black collector plates, and directly you have some copper tubes. Now, what do we know about copper, guys? Copper is a good what? What is copper?
A good conductor.
A good conductor, right? So if I were to attach the copper tubes directly to the black collector plate, which is absorbing most of the heat, and let's just say I'm running water inside the copper tubes, eventually that water is gonna get what? What's gonna happen to that water over time?
It's gonna heat up.
Exactly. Drew, does that make sense? Like if you have a black collector plate in a glass box, right? And you have copper tubes running directly against the black collector plate and you're putting water through the copper tube, wouldn't it eventually heat up?
Yes, sir.
So we understand the general concept of a solar water heater. Now, why does it work? So Drew, this is the exact principle. Again, the short wavelength radiation enters in, right? It heats up the black collector plate. It heats up the black collector plate, right? No. Drew, do you think the re-emitted heat is going to be greater than the energy that came in or less than the energy that came in?
Less than.
Exactly. So it's not going to be able to escape or penetrate the glass, right? So a short wavelength radiation is going to enter, right? And long wavelength radiation is going to be re-emitted. This cannot escape as it has low energy and it gets trapped. So over time, it just builds up, and that is the greenhouse effect there. So I would like you guys to, would you all be able to draw this? Or nah?
Yes, sir.
Yeah, okay,
Possibly.
possibly. Okay, well, take 7 minutes and copy this down, right? And if you have anything you don't understand at all, just tell me. But I think we understand the general concept. I'm going to read the model answer, right? Actually, Nikolai, read the model answer for me and see if you understand everything they're saying.
Alright. Shortwave radiation from the sun passes easily through the glass and is absorbed by the black surface. The black surface becomes warm, but because it is much cooler than the sun, it re-emits the energy as long-wave infrared radiation. Cooler objects always emit longer wavelengths of radiation. Long-wave radiation cannot escape back through the glass, so it becomes trapped and the temperature inside increases.
Did you understand everything that you read? Or was it like crazy?
Yep,
Okay,
nah, I understand everything.
okay, nice. Yeah, Drew, does the model answer make sense?
Yes, sir.
Okay, good. I hope you're seeing that
Oh,
physics.
sir, and
Yeah, talk to me.
short wavelength means high frequency.
Yes, yes.
Remember, I didn't do physics, that's why I just asking these questions. How about?
Look at all the relationships over here. All of the relationships are over here, right? You would learn this in Unit 1 physics. So, do you know what V is equal to F lambda? You ever see that in your life? V is equal.
Nah, never.
Nah, never.
Wait, let's see that only in physics.
Yeah,
Science didn't count.
I do think you'll see that in chemistry. Maybe if you're doing like mass spectrometry.
Which is oh yeah,
Okay.
I think we see it, but I don't think I was paying attention.
All right. So velocity is equal to frequency times the wavelength.
Oh nah, we didn't see that. None velocity.
All right.
But we did the atomic spectrum and stuff.
I'm pretty sure you might see E is equal to HF, right? Where E is
Oh
energy,
pla wait,
it is
yeah,
Planck
yeah, yeah.
constant,
Planck's equation.
right? And F is frequency. Maybe you might see that, right?
I wasn't paying attention at that time, but I heard of it.
Okay, okay. Well, good. So the velocity of the wave is equal to the product of the wave's frequency by its wavelength. So if it's a short wavelength, that means the wavelength is small. So let's make wavelength the subject of the formula. To do that, I will divide both sides by F. Right here. Give me a second. The wifey calling now. Hey boy, again, quarrel. Somebody want my Pomerock. Oh yeah, I go pick my Pomerock after class, boy. Good. I like Pomerock.
Of course.
Or if I tell you, I have like a huge tree in the back of my house. Yeah, I have a huge tree.
So my boomerang ain't been for the longest one.
Ways, boy. That's not real sad, boy. It
It
input
bear
that.
once and everybody eat it out. And then bear again.
They probably say, nah, man, these people too greedy. These people, nah, these people too greedy. I'll take on, I'll go eat something else. Anyways, so watch. Let's try to prove it mathematically, because Drew, I feel like you like maths. I love maths as well.
Wait, so you could just tell me what the F and the other thing means again?
Right. So V is the velocity of the wave, right? Velocity is the rate at which the wave is being propagated, right? Velocity of the wave.
Right. What does propagate mean?
Okay. Uh, how fast the wave is traveling. Like
Okay.
imagine a speaker generating a sound wave, like the rate at which
Mm-hmm.
it's being produced.
Okay. So how like fast the music being played?
I wouldn't say how fast the music is
Or
being.
nah. Nah.
Nah. I could give you another example, right? It's
I mean, I could understand how fast the waves moving, but I just was trying to compare it to something.
okay, it's a slinky.
Yeah.
Okay. Let me see if I can get an animation here. Animation of a slinky moving in a transverse manner. Right, so let me see if I can share this. So I feel like it's a visual example you need to see, right? Slinky. Do you know what a transverse on a longitudinal wave is by chance?
Sorry?
A transverse on a longitudinal wave.
No.
No? Okay. That's all right. I'm trying to find a GIF.
A GIF.
I just say GIF. Yeah. Um, trying to find one. Uh,
So you want me to just look it up?
okay, I find something. Space away. All right, so you see the arrow that says energy transport?
Yeah.
Yeah, that can be substituted with propagation of the wave. So like imagine if you move a slinky up and down, it would like it would it would start off flat and then the wave would propagate to the end. I really think you need to see it animated for it to make sense. Give me a second. Why is it so hard to find a reliable GIF or GIF or however they say it?
I watching that video on it and he just moving it from side to side.
Yeah, right to watch. So direction of propagation. I'm not sure if you could see what happened in there. That's like the direction in which the wave is gonna be it's gonna move and how fast it does that. So when I take the slinky and I move it up and down, the wave is gonna travel in this direction, right? And it's gonna
Mm-hmm.
propagate from left to right at a certain rate. That's propagation.
Where did left or right come from?
Okay. If you take the slinky, right, and you move it up and down, right? Isn't that wave
Yeah.
going to spread throughout from left to right? Again, you need to see our actual GIF for it to make sense. Give me a second. Is this a good one?
I said, don't worry, I'll go look at it after.
Okay, okay, I find one. I find one. Nice. I don't like confusion at all. I don't like when a student is confused. That's like mess with me. Like I can't sleep at night. So like if I explain
But I
something,
need to know this for CSEC.
yeah, yeah, you need to know this for C-sec. Watch, watch,
Oh,
watch.
shucks.
You see, like watch this. So we're traveling. So we're traveling. When the movie
Yeah.
you're going from left to right. Going from left to right. Propagation is the rate at which it moves from left to right. And you see, like when it hit the
So
corner,
like
yeah.
from left to right, when it peaks.
When you move it back and forth, it's gonna propagate from left to right. And when it hits the end, it's going to rebound and now go from right to left.
Okay.
You have a Slinky at home?
No.
Shucks. I will send you a video after this,
But,
right?
but like not talking about the wave, but like when the line it curves one way and then it curves the other way.
Well, if it's a curve the other way, it needs to reach the end, and according to Newton's third law, that says every action has an equal or opposite reaction.
Yeah.
Yeah, so when the wave travels to the other end, it's going to do the opposite now. It's gonna move in the opposite direction because every action has an equal or opposite reaction. So like when you move the slinky up and down, a wave is introduced and it goes from left to right. And when it hits the other end, it's going to rebound and it's going to go in the other direction. And I'll try to explain it better to you at some point. Yeah. Right. So
All right, all right.
just know that the velocity is how fast the wave is going to travel.
Mm-hmm.
Okay, the easiest example I could give you is like the speed of sound, right? Or like the speed of light. That's what I'm talking about. That's the velocity. Like how fast is the wave traveling? Like sound would travel at 300 and something meters per second. Light would travel by 3 by 10 to the power 8 meters per second. So it's how fast the wave is going to travel. That's what I'm trying to say. That's what velocity is. Frequency is how long it's going to take to make one full oscillation. Wait, no. Yeah, that's correct. Frequency is the time it's going to take to make one full oscillation in 1 second. In 1 second. So how much oscillations happen in 1 second? That's frequency. So do you know what an oscillation is?
I just know oscillation and fans,
Okay, well, you probably know that when you put the fan to oscillate, it is go from left to right and come back to its original position. And then repeat.
Yeah.
Okay, how much times is the wave repeating in 1 second? That's frequency. So like
Okay, yeah.
if that's a full wave, right?
So yeah, yeah. So a high frequency, the waves will be like more closer together.
Exactly.
Like it
Exactly.
wouldn't, yeah.
Exactly. Watch. If it took 1 second for a full oscillation, I'll say 1 hertz. Because in 1 second I had a full oscillation. Um, if in 1 second it had a half of a full oscillation, I would say that's 0.5 hertz. If in um if in 1 second it had two oscillations, I would say that's 2 hertz because there was two oscillations per second. So like that's what frequency is.
So higher frequency is more hertz.
Yeah,
That,
yeah, 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 yeah.
that makes sense. I think I heard that like in different contexts.
Right? And the higher the frequency is, the closer, the smaller the wavelength is gonna be. And wavelength is just the distance between um a successive trough or a successive crest. Or long story short, wavelength is the distance for one full oscillation. That's the easiest way I could put it. So like you see from here to here, that would be our wavelength. That would be the length of the full wave. Yeah.
Okay.
Right now we're doing waves and optics, which is the next topic. But that's fine. I mean everything in physics is interconnected. Long story short, v is velocity. That's how fast the wave's gonna carry. Wave's gonna be propagated, or in even simpler words, is how fast the wave is gonna travel. F is how much oscillations are gonna have in 1 second, right? And lambda is the wavelength. That's the length of one full oscillation. So V is equal to F lambda. V is equal to F lambda. If I were to make wavelength the subject of the formula, I would divide both sides by F, right? So I end up with wavelength is V all over F. So look at this relationship. Look at this relationship, right? The greater the wavelength, the smaller the frequency would have to be. See that?
Yeah.
Right? The smaller the wavelength, what would happen to the frequency?
It would increase.
Exactly. So that's why we're saying short wavelength radiation has a high frequency because it's a short wavelength, has a small wavelength. Understand?
Yeah, and high frequency means more penetration.
Yeah.
So higher hertz is more penetration.
Yep.
Okay.
You ever wonder why like high pitched music is like be piercing?
Yeah, I was now tying it into that.
Yeah.
So higher the pitch, it could damage your ears.
Well, it's gonna reach a point where you can't even hear it. But
Huh?
because humans could only hear between 20 hertz and 20 kilohertz. That's like the audible spectrum. We can't hear anything below 20 hertz and anything above 20 hertz. 20,000
So we
hertz.
just not hear it or do some test or something.
Well, if we go on like the low side, um, a sound wave of say 5 hertz at extremely like with a big amplitude, you'd feel it in your chest like an earthquake. And you'd feel it. You'd feel it. You wouldn't hear it, but you'd feel it. And if we go to the upper echelon, like hundreds of thousands of hertz, yeah, you wouldn't hear it. You mightn't even realize it playing. You know it's a dog whistle?
No.
Okay, do any of you guys here know it's a dog whistle? Nikolai, Ambika?
Yeah, yeah. It's a frequency. It's basically a whistle, but a specific frequency that we can't hear, but dogs can hear.
Yeah, exactly. And so like Drew, when you blow that, dog is like unbearable for dogs, but like we wouldn't even know it playing because it can't hear it. So you into music and stuff? Like car audio and speakers and whatnot? Or nah,
Not really.
not really. Well, bass is something you feel, so bass is like a low frequency. Nikolai, it sounds like you into car audio and thing.
Of course.
Oh, you gonna love my setup then. You gonna love my setup.
15s or
No, I have it in my room, but it's like 6 speakers. I have I have two 6 inch, two 4.5 inches. That's what mid bass. And highs
definitely.
and
That ain't bad. That ain't bad. That actually good.
and I
Because
have
if it's for room, yeah.
and I have a 12 inch right under a 12 inch
No, that when the real thing starting, yeah, 12 inch.
in a T-line box.
T-line. So you know, it ported is now open boxes or is that full close?
Oh, T-line means transmission line, it is ported, right? As we would know as ported. So the sound wave has to travel a certain distance to be displaced, so that when it comes out, it's gonna be in line or in phase with the wave created by the front of the speaker. So
Mm.
you're gonna love when we do waves on optics, right? You're gonna love it. The whole point of having a ported enclosure, Nikolai, is so that the sound wave in the back sound wave, because think about it, when the sound pushes back, it creates air pressure in the back, right?
Yeah, and that'll come out.
It had to come out, right? Now, the back sound wave cancels off with the front sound wave. That's why if you don't have a speaker in a box, it sounds horrible because there's destructive interference. But when you pass speaker in a ported box, the back sound wave has to travel some distance before it come out. And that kind of displaces the sound wave. So like now when it comes out, it's actually in line with the sound wave being produced by the front. And they combine. And that's why for some frequencies it's so impactful. Yeah. That's why you can tune into certain frequencies. To tune into certain frequencies, you have to either increase the volume or you have to increase the distance of the transmission line.
Mm.
Yeah.
That bad.
Yeah. But yeah, Drew, you're gonna feel Okay, below 20 hertz, you'll feel it. It'll be like a visceral feeling, right? You'll feel it in your chest. And structures might like break. High frequencies, you can't really hear it and it doesn't really do much. Yeah. But if we're talking about like 20 kilohertz, it's gonna be like piercing ears. Yeah. So Drew, you'll learn a bunch of new stuff. Before this, you probably would have never know that humans have like a certain range of hearing. Yeah.
Nah, I didn't know that.
Next time you buy headphones, look, I want you to look at the frequency range. You'll see most of them is like 20 to 20,000, if not in that spectrum. Yeah. Physics is so cool, eh? And Nikolai, I made an amplifier from scratch, as well as the power supply, like the circuits and everything.
Big man thing?
Yeah, yeah.
Eee!
I was doing electrical engineering, like I doing my degree, my bachelor's degree in
That's
computer.
why I doing that all. But I not doing it like your level, I doing it at the starting level.
Okay, okay. Yeah, because like the level as we doing stuff is like, oh, it's giving my headache. I like it, but it is giving my headache. It's giving my headache.
But really, right now when we reach in school, that is still headache, but they don't have me doing all kind of math thing.
Oh, well, I feel like you go like the electrical part of physics. You go love it. You go love it. Right? But yeah, so Drew, this is a mathematical relationship. So if you make wavelength the subject of the formula, you will see that wavelength and frequency is inversely proportional to each other. You see that, right?
Yeah.
And you remember like constant of proportionality, like inverse directly proportional. You know what I'm talking about? Like
Oh, I don't know.
if I tell you frequency is inversely proportional to wavelength, right? F is proportional to 1 over wavelength, and then you would
Yeah.
use the constant of proportionality, right? Over here, the constant of proportionality is velocity, because it's in the same position. You'll learn that in C-Sec maths at some point. Probably forget it,
To
but
be honest, nah, I didn't learn that.
it is, boy. That's on the algebra. That's
I
on the
think I
algebra.
was supposed to because we didn't finish the syllabus, to be honest.
Hey, boy. And it's all like
I
somebody that
still I
likes to
still get
learn.
my I still get my distinction, but like we didn't finish it because what had happened was my teacher did pass away.
Oh, shucks.
So he was without a teacher for a little bit.
I thought you was gonna say a teacher got pregnant, because that's usually what has happened, right?
Nah, she was a kind of old lady.
But I'm sorry to hear that. R.I.P. Hey, boy.
Yeah. She was real fun though. I'm funny.
That's good. That's good. Sound like she make an impact.
Yeah.
We still get a distinction, so win-win, you know? We still get
Mm-hmm.
a distinction. Right? So I will I'm gonna give all some chance to copy this down. Right? You should see the screen any minute now. Copy this down. And we're gonna start gas laws. Why is it doing that? It like keep disconnecting. It's weird. Something wrong with the cable. I know the laptop is not a problem because like it's a new laptop. A high-end one. So it's not supposed to be giving trouble. And it's like an iPad, like I don't know why it's giving trouble. How to be the
So
cable?
what specs you have?
Is a M1 Max with 64 gigs of RAM.
M1 Max.
Yeah.
Was that? That's the model?
No, that's the CPU. It's Apple. It's not
Oh,
yeah. Yeah, it's Apple. I don't like Windows. I've
oh
had I've had,
nah.
I've had my run-ins with Apples. I mean I've had my dealings with Windows on it. It just like
Wait, what
compared
Windows do though?
Really, what windows do you?
like if I show the performance in this MacBook, or it would be like damn. Like I could emulate
When you
games.
say
Yeah,
you emulating games?
I could emulate games. I could run a Zoom meeting. I could have multiple streams at the same time. I could do all of that.
Yeah.
I could do all of that without being hooked up to the wall, and the battery would last me like 3 to 4 hours.
Wait,
Under
so
all of
that
that.
laptop is stuck or you mod it?
It's stuck. It's stuck. Like you don't really mod anything with Apple. Like Apple MacBooks, like
Ah,
you don't mod anything. It just like
I
goes.
know it's have people who does add real RAM and change the SSDs and thing to the laptops.
Oh, you can't do that with MacBooks. Because everything is soldered onto the board. Like, yeah.
Shucks.
I mean, you could do it.
Yeah, graphic cards on that.
Say that again?
Yeah, graphic cards or they don't run that.
Okay, the graphics card in this is integrated into the CPU.
Oh
So
Mm,
my
like
days.
it's not
Jesus.
it's not it's not like a separate graphics card. It's built in into like one big chip, but it's really powerful. It's really, really powerful.
How much cores it have
This
in the
have
CPU?
Yeah.
this have 10 cores in the CPU and 32 GPU cores. Yeah.
And what's the gigahertz?
The gigahertz is not so important. I think it's like 3 point something, but the memory bandwidth is like 400 gigabytes per second. It's like insane.
Nah.
It's like
400 gigabytes.
per second. Per second. That's the speed at which the memory moves, the RAM.
I just check that.
Look it up online. Just look up memory bandwidth. I think VRAM, which is RAM for CPUs and GPU. Oh, no, I think the RAM for GPU. I don't know if you know about VRAM, but VRAM is supposed to
Yeah,
be
VRAM.
VRAM is supposed to be really, really fast. But what Apple did, they actually made one big chip, and that one big chip has a CPU and a GPU, and it takes from a pool of incredibly fast RAM. So this RAM is incredibly fast. You see, the thing is with Windows, you would have the GPU separate, you have the CPU separate, and it have to travel back and forth. That introduces some like delay. But with this is like there's no switching. It's just like, okay, I want 16 gigabytes of RAM. Okay, take it. Yeah. But like,
The memory bandwidth determined by the supported RAM specifications.
yeah, I believe so. Like, just look, like if you're interested in seeing the speed of like a crucial RAM stick or something, just look up memory bandwidth for it. Memory bandwidth for DDR5 RAM.
But you had DDR5?
No. Hear this, right? Let me put something into perspective here. So DDR5 RAM has a memory bandwidth of 38.4 gigabytes per second. The RAM in this is 400 gigabytes per second. Yeah. And in newer MacBooks, 600 gigabytes per second. It's insane. Like people is rarely sleeping on MacBooks. The only reason why
I
people
don't know if I trust that, you know.
Really?
no, like it's insane.
Cause my cousin had a MacBook and it was kinda tutu, I don't wanna lie.
Okay, I'll be honest
But
with
I
you, right?
don't hear much good things about MacBook before.
No, I'll tell you something, right? I had a 2019 MacBook. I had a 2019 one, Mac spec. Like, but I was an Intel machine now. And in 2020, Apple introduced their own chip, the M series chips. And wow, it's like night and day. It's like night and day. So like all MacBooks before 2019 and 2019 is like garbage. It's like you're not worth it. Everything after though is like wow. It's like S-tier. It's insane. Yeah, I tell you, like I could do all of those things on battery, I don't hook it up to the wall. It's crazy. Yeah.
The M1 Max better than the M2?
The M1 Max is roughly on par with the M3 Pro. The M1
So
Max is
better than the M2.
better than the M2. I have an M2 in my iPad. It's better. This scores anywhere between 13,000 to 13,500 Geekbench. This is like a older generation model. The newer generation MacBooks score like 26,000 in Geekbench. I'm a
Yeah, but how
laptop.
much you pay for this?
I paid 10,000.
Oh
And
my days.
What?
and it was used as well.
You
A brand new one would have been
you
a lot more.
dropping 10 bands on a laptop when you could buy a car. With a
Hold on. Not only that, let me take you some into consideration, right? You could get a used B14 and still have enough money to go and at least buy one box of music and you buy it on a laptop?
Yeah, because this is my living. This is my livelihood here. Like Oh, they don't understand. If you're
Wait,
full,
you could have buy a whole gaming PC setup, you
Telling
know.
you, dog.
no. If all you have this, all you gotta understand, like it's just insane. Like imagine having that gaming setup and you could carry that wherever you want, and the fan doesn't even make noise. Like
Okay, making
battery,
up your point now.
like okay, the fans in this almost never come on, and the temperature is usually like 60 degrees Celsius for the hottest. It is insane. It's insane. And the battery lasts all day, right? It is insane, guys. The display has essentially like a 4K display, which is essentially OLED. It is insane,
Wait, what's
guys.
the hertz?
120. 120.
All right.
Yeah, it's like a whole workstation in one. If you were to buy an equivalent monitor, right? The equivalent setup, it'd be like it would not be as compact and it wouldn't be as integrated as this for the price. Like it just do everything in one. Yeah. The new MacBooks cost like 26,000. Yeah. But like
That's
this
so crazy, but that's
look
too overpriced.
now like
Yeah.
all you gonna see that until they use one and it's like, oh, because my friend he has a HP Omen, which he paid 1750 US for, which is more than the laptop I have. His laptop can't play Asphalt 9 without making extreme amounts of noise, and it throttles if it's not hooked up to the wall. I could play Asphalt 9 on max settings while doing multiple streams, while having a video editor in the background, and I could do all
So
of this.
you had to run like Elden Ring.
Okay, that's the next thing, right? MacBooks are not
Check
made for gaming.
Horizon 5.
Like, you see, MacBooks are not made for gaming. Most games are not supported. You could emulate them, but it's not gonna run as good as a dedicated gaming computer. Because MacBooks are made for work and productivity. They're not really made for gaming. You wouldn't buy this machine to game. You buy it for your business, like creative work, video editing. Yeah.
So like yeah.
Like this whole laptop is for streaming, video editing, photo editing, simulations. It's not really for gaming, but I can handle gaming really well. Yeah.
It's like, yeah, separate laptop for that. You just run everything on one.
I don't play games. My game is life. I leveling up in life. I don't play virtual games. You know, this
I
is
like that one, but
this
I
is the
taking that
game.
from you.
This is the game. Life is the game. And if you're not doing things in the real world, then nah. You're gonna spend time building a virtual world? Nah. I want to build a real world. So I just use this laptop
Yeah,
for
but Elden Ring though.
I don't play games. I don't play games. I don't play games. Yeah. I genuinely don't play games. So if you all were to buy the MacBook, unless you're doing serious work with it to make money or like as an investment, you might find it like you waste money. But for me, it's gonna pay back itself very soon. It because I was being held back. Imagine having live streams and I have like over like 200 people like joining a Zoom meeting, and you can't do a YouTube live because your laptop holding you back. But with this, I could do all of that. It yeah. So it's gonna pay back itself. It's fine. At 10,000 sound like a lot, but when I start working and you start spending money and you start making money, you'll be like, okay, that's not that bad. Because when I was
Yeah,
about
true.
say that again?
I say, well, that's true because when you really watch it, depending on how much you work for, minus tax, and if you're training and thing, well, you're saving extra money there.
Yeah, exactly. Well, before you have children and thing, like let me just say you start working. Um, because I grinded for a month and I bought this money strictly from the money I made in a month. I didn't dig into my personal money. It was just the business money, and I got this in a month. But talking about like no sleep kind of grinding, like every single day is insane. But when I started working, I like realized 10,000 is really not a lot. Something go wrong with your car. I don't know, like a 7,000, 6,000. It's crazy the cost
Well,
of living these days.
now the tickets and all go kill you before your car kill you.
Yeah, what? Coconut Vanda, you see that? It's crazy.
19,000 a boy get.
Yeah, boy.
You
That's
you
crazy.
into drop low cars and thing, or you just like the audio system? Right.
I not really into drop low cars and thing. I into like okay, I into like under like I don't even know what I'm talking about, like the underglow. I like that.
Yeah, on that glow, the door one and thing.
Yeah.
But as they say, I could hit you with a story. When these laws come into place, I have a friend who brother have a car like a drop and everything. He get fined 26,000 because the car was dropped. It had underglow, the door had lights, the fine him for everything. Dark outings, music. The music boxes, they strap one onto the other. So it pushing the roof a little bit. So they fine him for everything. He lights everything.
Wow. Drew, you drive? Oh no.
I ain't get my license yet.
You got your license yet?
No.
Nah, don't worry. Well, the rate thing's going. If you do get it, you might be a little hesitant to go on the road. Like right now, I fixing up my vehicle and I kind of worried if I go on the road and I get a fine. Yeah, it's kind of crazy what's going on these days. And the thing is, the lawless people that
Yeah.
get through it, like the lawless people that get through. I don't understand it. I don't understand it. You go like
You
just
gonna
drive.
put your music in your car?
Say that again?
You gonna put your music in your car, or you're leaving it in your bedroom until like
Mm.
you're ready for it.
Well, you see, the that car is really my grandma's car, right? But she's transferring it to me. She's giving me in. So I don't want to make too much modifications to it, right? I want to keep it the way it is for now until like I buy my own vehicle, right? So for now, I might just buy like a JBL, like a Extreme or something, and just fit in the car for now. But yeah, Nikolai, I'll send you a video of the sound system I have. But anyways, um. I'm not sure if I'll copy this down, but before class finish, I want to just run through the gas laws. There are three of them, and you need to know all three, right? But hopefully, let's see how much examples physics have. It can apply physics to everything. Like physics is goated. Physics is really, really cool. You can't hate physics now. You can't hate physics. If you do, then that's tough. Okay, let's try to understand one of the gas law without even looking at the formula, right? Let's look at pressure and temperature. Talk to me, guys. Drew. Drew, talk to me, right? You know it's a pressure cooker?
Yeah.
Okay, you think the pressure inside of a pressure cooker is high or low?
Hi.
High. What do you think that does to the temperature inside of the pot?
It decreases the temperature.
Decreases? No.
No, it increases it. My bad.
Because think of it, right? If you're building pressure inside, all right,
Hmm.
you're trapping all of the energy inside and the molecules. Okay, remember the kinetic theory of matter or not?
Um, yeah, that molecules in constant motion.
Right. Now I have a question,
Is
right?
that?
Yeah. I have a question. Right. So long story short, pressure and temperature is directly proportional. So if pressure increases, so does the temperature. If temperature increases, so does the pressure. Let me explain why. Nikolai and Drew and Ambika, all they ever leave a Coke in the sun, like a carbonated beverage in the sun before. Have you all ever done that?
Yeah.
Yeah. When you go to feel the bottle, is the bottle soft or very, very stiff?
Stiff
Right. So did the pressure decrease or did the pressure increase?
increase.
Right. Let's try to understand why. When you add heat energy to matter, what happens to the molecules on the inside? They gain what type of energy?
Kinetic.
Exactly. They gain kinetic energy. Nikolai, do you know what kinetic energy is?
I think so. In kinetic energy is energy that you just do like with movements and thing.
Yes. So if an object is moving, it has motion, then it would contain a certain amount of kinetic energy, right? So bodies in motion have a specific amount of kinetic energy. the more motion the body possesses, the greater the kinetic energy. So, long story short, guys, when I apply heat, right? Let me just put this in a box. Right. So, guys, if I apply more and more and more heat, wouldn't these molecules gain more and more kinetic energy?
Mm-hmm.
And if they gain more
Yeah.
and more and more kinetic energy, they'll want to move and vibrate, right? So eventually they'll break away from the bonds and they will start to press against the walls, right? Now, if you have a fixed container, right, and these molecules vibrating and moving about real fast, wouldn't they hit against the surface and press against the surface because they have so much energy they want to escape? Tell me that
Yeah.
makes sense. Nikolai, if I keep adding energy to the system, wouldn't the molecules start to move and vibrate and hit the surface,
Yeah.
hit the walls? Right.
Yeah, there was a little was
They start to hit the walls. And Nikolai, if they're hitting the wall with some force, do you think the pressure is increasing or decreasing?
increasing.
Right, because you're pressing against the walls. You want to move, you want to escape, right? But the pressure is starting to build up on the inside. So long story short, when pressure increases, temperature increases. When temperature increases, pressure increases. Do we understand that?
Yep.
Yeah. Right, Andrew? If one thing increases and the other one increases, they're said to have a what kind of relationship? Directly proportional relationship or inversely proportional relationship?
Directly proportional.
Right. And we could prove it quickly, right? So pressure is directly proportional to temperature. So the initial pressure will be proportional to the initial temperature. And guys, if you leave a bottle of Coke in the sun, will the temperature remain the same after you leave it for some time? Talk to me, guys. If you leave a bottle of Coke in the sun, is the temperature going to remain the same?
No.
No, the temperature is going to increase. And if the temperature increases, wouldn't the pressure also increase?
Yeah.
Yeah. Now, I teach you some maths here at the same time. By the way, I teach maths for in any maths class. Check ma, right? But they are proportional. So if anytime two things are proportional to each other, you have to introduce a constant of proportionality. So I can write this as P1 is equal to K by T1. So K is the number linking P1 and T1 together, right? Nikolai, way to apply the same concept here, right? So, wait, let me just switch this around, keep it consistent. Yeah, so Nikolai, over here, I could write P2 is equal to what?
P2 is equal to KT2.
Exactly, right? Exactly. Now, if I were to make K the subject of the formula here, what would I have to do on both sides, Nikolai? If I wanted to make K the subject, so I wanted K to be the only thing over here. Or would I need to cancel off here if I want K to be the only thing over there? Or would I need to cancel?
Cancel the 1 and T, it's NP.
The T1, right? T1 is a term by itself, right? And T1 just means the first temperature, the initial temperature. So you're saying I'll have to cancel off this, right?
Yep.
To cancel off that, what would I need to do on both sides? Right now, K is being multiplied by T1. What is the opposite of multiplying by T1?
Divide. Yeah,
Right?
divide.
So I'll divide both sides by T1, right? That's what I'm going to do. This and this is going to cancel off, and I'm going to be left with K is equal to P1 all over T1. So guys, keep that in mind, right? Remember that. Actually, I'll leave it like this. I'll say equal to K. Drew, did anything confuse you there?
No, so
All right, well, let's make K the subject of the formula for this, right? Same process, K would be equal to what?
P2 divided by T2.
Exactly. So K is equal to this, and K is equal to this. So long story short, Drew, K is just a ratio between the pressure and the temperature, right? And the ratio is supposed to remain the same. So you know what I could do? If both of them are equal to K, what equation could I make? Both of them are equal to K. So what equation could I make?
What do you mean, what equation?
Okay, you know about um a substitution. You know about that?
Yeah,
I want to apply the same concept here. What is K equal to here?
a constant.
Yeah, P1 over T1, right? K is equal to P1
Yeah.
over T1. So if K is equal to P1 over T1, right? Then K is equal to K. So P1 over
Eh,
T1 would be equal to what?
Oh, P1 over T1 is equals to P2 over T2.
Yep. And believe it or not, we just actually came up with a gas law from scratch. That wasn't that hard. And it's the same process for all the others. Right? Yeah. So the specific one we would have looked at, right? Where is
The
it?
pressure law.
Yeah, the pressure law. Right? And the other ones is Charles' law and Boyle's law. So let's look at, so this is the pressure law, right? This is just simply the pressure law. Right? So the pressure law is just P1 over T1 is equal to P2 over T2. If you want, take a copy down the full working, but this is what you need to know for the exam. P1 over T1 is equal to P2 over T2. Right? You need to know that. Okay. Now let's look at Boyle's law. So Boyle's law deals with pressure and volume. Right? So Boyle's law. It deals with pressure and volume. Nikolai, do you think pressure and volume is proportional or like inversely proportional? If you had to say.
I think the proportional.
Yeah, sure. Nikolai,
Mm,
to
yeah, what it?
think about it logically, right? When you squeeze a bottle, are you increasing the volume or decreasing the volume?
No, I decrease in the volume, so then it's proportional.
And when you decrease the volume of the bottle, the pressure does increase or decrease?
The pressure will decrease.
Pressure will decrease.
No, like when you like while you're squeezing it, oh,
Now while you're squeezing the bottle,
yeah, the pressure will increase.
increase, right? Drew, does that make
Yeah.
sense? Drew, if you're squeezing a bottle, you're decreasing the volume, and by decreasing the volume, what is happening to the pressure?
It's increasing.
Exactly. So do you think, so here what? While I decrease the volume, what is increasing?
Pressure.
So is it proportional or inversely proportional?
Inversely.
Exactly. So instead of me writing P is proportional to V, I will now write P is proportional to actually 1 all over V, which means that they are inversely proportional. That's what it means, right? Because Nikolai, and when you decrease the volume, what does increase? When you drop the volume, what does increase?
The pressure.
Exactly. So Nikolai, if I make the volume smaller, what would happen to this fraction? Will it get bigger or smaller?
I think we're getting smaller.
Nah, it would actually get let me show you some
Bigger.
yeah, let me show you some actual calculations to back my claim, right? You can see it better with the numbers. So what if I told you the volume? What if I told you the volume was 10 centimeters cube, right? Actually, let me use meter cube. I want to keep with the SI units. Yeah, let me keep with the SI units. Yeah, so Nikolai, let's look at two scenarios, right? I tell you the volume is 10 meters cube, and in the other example, I tell you that the volume is 0.01 meter cube. With me?
Yep.
Where is the volume more? 10 meter cube or 0.01? Where is it more?
Is more. The volume is what?
Where is the volume greater? In 10
At the
meters cube.
10.
Okay. So watch what's gonna happen, right? So I'm gonna put 1 over 10, right? 1 over 10. So 1 all over 10, right? I get 0.1, right? I get 0.1. I want you to keep that in mind, right? So when the volume was
Like,
10, I got a pressure of 0.1 pascals. Let me try 1 all over 0.01.
100, yes?
Yeah, 100. Because, okay, and a logical way to think about it, right, Nikolai? If I put 1 over 0.01, isn't 0.01 very small?
Yep,
So wouldn't you need a large amount of 0.01s to make 1?
yep.
Yeah, you would actually need 100 0.01s to make 1. So long story short, Nikolai, the smaller the number here, what's going to happen to your pressure? It's going to increase or decrease?
It will increase.
Exactly. The bigger the number here, your fraction is going to be small, so your pressure is going to decrease. So anytime we talk about inverse proportionality, you need to write one quantity is proportional to the reciprocal of the other quantity. So I wouldn't just write V, I'd write 1 over V. Right? And you'll have to learn this in maths as well. Right. So Drew, you understand this, right? You understand why we put pressure is proportional to 1 over V and not just V?
Yes, sir.
All right, would. So in the next line, I'm going to introduce my constant of proportionality. So just like in this example here, I said P1 is equal to KT1. Over here now, I'm going to say P is equal to K all over V. Now let's look at two scenarios. So Drew, let's look at a scenario where we have an initial pressure and an initial volume, so P1, V1, and let's look at a scenario where we have a second pressure and a second volume. So Drew, maybe the initial pressure and initial volume would be the pressure and volume of the Coke at rest, and maybe the second pressure and volume would be after you squeeze it. Right? You got me?
Mm-hmm.
Just, I hope I'm not confusing you. So I'm saying that the first condition is initial, like it didn't do anything. And I'm saying that
Yeah.
the second example is after you do something with it. Either you increase the volume or you decrease the volume, right? So talk to me.
Mm-hmm.
P1 would be equal to what?
K over V1.
Right? If I were to make K the subject, I would multiply both sides by what?
V.
V1, right? And
V1,
so
sorry, yeah.
I would get P1, V1 is equal to K, yeah?
Mm-hmm.
Let's look at a second condition now. So P2 is equal to K all over V2,
Yeah, I seen it.
and that'll be P2 V2 is equal to K. And both of them
Yeah.
are equal to K, so I could now form an equation. What equation would I form?
P1 V1 is equal to P2 V2.
And we just came up with the Boyle's law from scratch, right? Which is this law over here, right? And that's why
Mm-hmm.
P is equal to K. So if you understand this, this is Boyle's law. So let me just highlight it. So this was the pressure law. So the pressure law is P1 over T1 is equal to P2 over T2. Boyle's law is P1 V1 is equal to P2 V2, right? So that's Boyle's law. The only other law we have to look at now is Charles' law. So Nikolai, if the pressure law was pressure and temperature, Boyle's law was pressure and volume, what do you think Charles' law is?
If you could repeat that one more time, please.
Right. So Nikolai, the pressure law, we're looking at pressure and temperature, right?
Right.
In Boyle's law, we're looking at pressure and volume. What do you think we will be looking at in Charles' law? Which is the last law that I need to know.
Pressure and energy?
Nah.
Nah, no. Right, pressure and volume, pressure and temperature. Volume and temperature?
Yes, you hit the nail on the head, right? Great. Nikolai, it sounds like you have some potential for physics. That's good, right? Feel like you'd like physics. I feel like you I feel like you have no reason to hate it. Because physics is very cool. Especially the things you could do with physics. Right? So on to Charles' law now. If anything, the hardest part of physics might just simply be the maths. But You had to work on the maths anyways, right? So it should be fine. So Charles' law, right? So Charles' law relates volume and temperature, right? So volume and temperature. Talk to me, Nikolai. If you, what is the relationship here? If I increase the temperature, what's going to happen to my volume? Think of a gas. Think of like a hot air balloon.
If they increase it, if they increase the temperature, then the volume will expand.
Exactly, because when you talk to me, right, Nikolai, when you apply heat to say a gas, the molecules are gonna gain what kind of energy?
Kinetic energy.
And when they gain kinetic energy, they're gonna start to move about very frequently. And they're gonna collide and they're gonna start to take up more volume. So as temperature increases, the volume increases as well, right?
Yep.
And you can think of a hot air balloon, right, guys? When you when you see a hot air balloon, isn't hot air being well, it works because the hot air rises and it goes into the balloon, but a hot air balloon, isn't the balloon like fully inflated? A little thing that's interesting that for a hot air balloon, like it not sealed, you know, it not sealed. It not sealed. A hot air balloon is not sealed. Have you ever seen like a hot air balloon before?
Excuse me.
Yep.
Yeah, like at the base of it, you just have like a flame blowing hot air into the balloon. And the hot air rises and it takes up space, and that's going to inflate the balloon. Because remember, Nikolai, as temperature increases, the volume increases. So that heated gas is going to take up space and it's going to inflate the big balloon. You see how all of this could be related to real life? It's one of those subjects that actually relatable and you could actually make sense of it. You know? All right, so I find like a good picture here. Yeah. Hey guys, are you seeing that?
Yep.
Yeah. Oh, you can see that, right? So can we see that heat, like a literal flame, is being propelled into the balloon? Can we see that?
Mm-hmm.
Right. So, Nikolai, when this flame over here, wouldn't it heat up the surrounding gas?
Yeah.
And what do we know
Heat up
about
the
hot
sugar.
air? What do we know about hot air? Does hot air sink or does hot air rise?
Hot air does always rise.
Right. So, oh, that's- so the hot air is gonna rise and it's gonna take up volume inside the balloon, and that's why it expands. So I hope you understand the concept. Right. So long story
I
short,
was
yeah, say that again.
no, I always saw that the heat used to just come out through the bottom. So that way you used to like propel itself shooting up.
Oh no, 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 no. And the reason why it actually floats, right, Nikolai, is because okay, if I told you that air is a fluid, that would sound kind of crazy, right? Like you probably wouldn't believe me if I tell you air is a fluid.
I, I would believe it because I had an interaction with something like that already.
The easiest example is to think of like hot air and cold air. Like, and if you go close to a room where there's air condition, like you literally feel the air flowing at your foot, like you're feeling it, right?
Mm-hmm.
You know what I'm talking about? It just feel like a liquid, literally
Yeah, it's
flowing.
like water, like cold water.
Exactly. That's because air is a fluid. Now, long story short, guys, if you take something that's less dense and you put it in something that's more dense, what's gonna happen? Guys, if you take something like
Uh-huh.
if
Yeah.
you okay, imagine you take a inflated ball and you
It'll
put it on
float.
water. It will float, right? Nikolai, and if you take something that's less dense, right?
Mhm.
And you put it on something that's more dense, wouldn't it float?
Yeah, it will float.
Exactly. So when you have such a large volume of air, do you think air is dense or less dense?
Air go be less dense.
It would be it would be very like it wouldn't be dense at all, right? And
Nah, air would have to be dense.
exactly. And when you heat up the air, do you think the density of the air is increasing or decreasing? When you heat up the air, think about it. The molecules moving all over the place, it's spreading out.
Increasing,
Now, is it decreasing or increasing?
increasing.
Nah, talk to me, right? If something is dense, then it's taking up a large amount of volume. What was I saying? If something is dense, it's taking up, it has a lot of mass in a small volume. But Nikolai, when you apply heat to the gas, right? When you apply heat to the gas, are the molecules getting closer and densely packed together, or are they spreading out and moving apart from each other?
Nah, that's for the not moving.
Exactly. So I have a question, guys. What do you think is denser, cold air or hot air?
Hot
Cold
air.
air.
I hear two different responses, right? Long story short, hot air is less dense than cold air. And guys, the reason is when you heat up air, right, you're adding kinetic energy. So the molecule's gonna move apart and they're gonna take up and they're gonna like spread out. And they're gonna be less densely packed. Nikolai, could you visualize that? Like you applying heat, right? So the molecules spreading out and they're moving all over the place.
Yeah.
So are the molecules getting closer together or are they spreading
Nah,
out?
they're spreading apart.
Exactly. So Nikolai, long story short, which one is more dense, hot air or cold air?
Cold air.
Right. So when you heat up the air and that hot air goes into the balloon, right? You are actually making that air less dense than the surrounding air. And you know what happens? If you put something less dense in something that's more dense, what's gonna happen?
It will float.
Exactly. So by you heating up the air, you're making the air less dense than the surrounding air. So it actually starts to float because it's less dense now. That's how it is work. The same principle like how a water balloon, I mean like a inflated ball with floating water is the same concept. Same kind of concept. By you putting hot air into the balloon, you're lowering the density to less than the surroundings, and as such, it could lift, it would float, it would rise. The more you know, right? So yeah, I don't think you'd have figured out that, Nikolai. That one interesting, right? It actually floats because of density, not because it has something like literally propelling it upwards. Density is why. You think you'd have figured out that one? Or you'd have always probably think it is like the fire propelling it upwards.
Honestly speaking,
Yeah.
it would be like one day I go believe this and the next day I go believe something else.
Oh. But that's the truth of it, right? It floats because of density. It floats because you're making the air less dense than the surrounding air. So if something is less dense and you place it in something that's more dense, it's gonna rise. It's gonna float. Right? So let me get back to this, right? So Nikolai, volume is proportional to temperature. So my first line is gonna look like V1 is proportional to T1, and then I'm going to write V1 is equal to what? Look at the past examples. I'll say V1 is equal to
V1 is equal to, well, yeah, it will be V1 is equal to T is equal to what? T1?
nah, K T1.
Mm.
Okay, I'll explain this in a way that will make sense, right? A way that you understand. Um, Hooke's law, you ever do Hooke's law before?
Yeah,
Okay, the more force you apply, what's gonna happen to the extension? The more force you apply, what's gonna happen to the extension?
the extension will be longer.
Right, but do all springs have the same stiffness?
Nope, they vary.
Exactly. So K is what links the force to the extension. So K describes how stiff the spring is. So it wouldn't be the case for all springs. So like for one spring, maybe I might apply a certain force and it would extend a certain way, but that wouldn't be the case for all springs. So that's what K does. Anytime you have two things related to each other, right? You need a constant that ties them together. So Nikolai, you see how force is proportional to extension? Over here, volume is proportional to temperature. And they'll be linked together by K, which is the constant of proportionality. That's actually what linking V1 and T1 together, right?
Mm.
The same way how F is equal to Ke, and K would correspond to the stiffness of the spring, right? Okay, so Nikolai, let's make K the subject here now. To make K the subject, what do I have to do on both sides?
You gotta cancel T, which means you gotta divide T by each, T1 by each.
Right? So we're going to end up with V1 over T1 is equal to K, right? And let's look at our second condition now. So V2, T2. If this is the case, V2 is going to be equal to what?
V2 will be equal to KT2.
Right? And well, you had to make K the subject again, so divide by T2,
Mm-hmm.
right? So V2 over T2 is equal to K. So you notice that both of them equal to what?
K.
Right? So if both of them equal to K, I could now say that V1 over T1 is equal to what?
K.
Yeah, but both of them equal to K. Both of them equal to K. Both of them equal to K, right? So I could say V1 over T1 is actually equal to what?
V1 over T1 will be K. K1.
Nah, like both of them equal to K, right? Both of them equal to K. So if I wanted, if you wanted, right, you could literally do this. Watch this.
Alright, that's different. Just putting them behind me.
So V1 over T1 is actually equal to what?
V2 over T2.
Yes. Right? V1 over T1 is equal to V2 all over T2. Great. And I'm showing only this because if all they figure it's in the exam, at least you can come up with it and still get some higher marks. Right? So yeah, guys, that is Charles' law, pressure law, and Boyle's law covered. This is the pressure law, this is Boyle's law, and this is Charles' law. Yeah. So you can take a screenshot of this and copy it down in your book. So you need to know this formula for pressure law. You need to know this formula for Charles' law, and you need to know this formula for Boyle's law. So yeah. Right. So yeah, guys, I will send these notes.
Yeah, I screenshot.
But that's it for class today. The next class we'll do some gas law questions, and hopefully we can move on to waves and optics. Right? Great.
Yes, sir.
Yeah, guys. So hopefully have a blessed night. Later, everybody.
You too.
Sir,
Yes.
yeah, I wanted to talk to you.
Okay. Let me just stop the recording there. Give me a second.